Hi. In this lesson, we're going to talk about the effects of magnetic fields on moving charges. To this point, we've talked about what happens when a charge is moving through a wire. And when that happens, this wire will get a magnetic field in this circular direction around the wire. So in the case of this picture here, we have an electron that is moving from the right to the left. And our first hand rule will tell us that the magnetic field around this wire kind of does these circular concentric circles around the wire. The question is, what's the purpose of the wire? What is the wire really doing for us? And it turns out that the wire really is not doing anything in terms of creating this magnetic field. It's simply the moving electron that causes the magnetic field. And so if we remove the wire, but still allow the electrons to flow, we will still get the same magnetic field. So consider this charged particle moving with its velocity, in this case from left to right. We can imagine that a magnetic field sets up around this thing, again, according to our left-hand rule, that will tell us that as this electron moves to the left, if we point our thumb in the left direction and wrap our fingers now, not around a wire, but around this charge, you get this magnetic field that's indicated in the picture. So just take a second and confirm for yourself that when you wrap your left hand with your thumb pointing to the right, that you do indeed predict that the magnetic field will be in the direction indicated in the picture. So that being in the case, we're going to take it one step further. Imagine now that the electron that we had pictured here moves not through empty space, but moves towards a region that has an external magnetic field. So I've pictured the external magnetic field with these light blue arrows, and the electron has a velocity vector that moves it from left to right. As that electron moves towards this region and into this region, its magnetic field, I haven't pictured it here, but you can imagine the magnetic field around this electron. The magnetic field of the electron will be influenced by the external magnetic field that it's traveling through. And as a result, as this object travels from left to right, it will feel a force on it because the two magnetic fields interact. So here is the third hand rule that allows us to predict how the interaction between that external magnetic field and the magnetic field of the charged particle, how that results in some sort of force. So stated in words, the hand rule would say that if you hold your hand in this kind of orientation here, fingers out, thumb up. So key here is that the finger and the thumb are like 90 degrees to each other. So when you're done here, fingers in one direction, hand in the other, but there's a 90-degree kind of angle between those two. So as I'm talking, just put your hand straight out, palm out, hold the, if you're using your left hand and you're looking at the back of your hand right now, you should see an L on your hand. And if you do that, then your thumb will be in the direction of current flow if we do this right. Fingers will indicate the direction of the magnetic field, and then your palm will indicate the force. And in this picture, they kind of have this result where because the thumb is up, the magnetic field is to the left, the palm ends up facing what they would describe as out of the page. Now, obviously, we kind of have a three-dimensional thing going on here, and it's at this point where it's going to be necessary to represent vectors that are not just in the x and y, but also kind of in the z plane or in or out of a page. And so these are the conventions that we'll use when it comes to vectors that are possibly into or out of a page. In the case of a vector that's into the page, we use this kind of circle with an x on it. If it's out of the page, it's kind of like this circle with a dot on it. And to me, this kind of makes sense. If you think about how we represent vectors, it's always with like vector arrows. So this would be an arrow to the right. You kind of have this point of your arrow right here, and you have the tail of the arrow here. If this was real life, this arrow might have some flights on it, some little feathers that allow it to go straight and true as you launch it. So in my mind, this makes sense if you consider that this might be what you would see if you fired an arrow out of a bow and you were looking at the back of it, you would see these feathers or these flights that keep it stable as it flies. And if you had an arrow shot towards you, you might see the tip of this arrow coming at you as it was moving towards you. And so when we think about vectors being represented by arrows, this idea of the arrow moving away from you or towards you kind of is consistent with what we've done so far. So let's take a look at an example of this then. Here we have an electron moving. Again, this is trying to show kind of a three-dimensional view, so you gotta kind of use a bit of your imagination here, but the electron is basically moving, I would say, to the right, but they're kind of showing it towards the bottom of the image a little bit to show you that it's kind of moving so that we can show another plane. But this electron's kind of moving towards the right. The magnetic field, consistent with what we've known before, is moving from north to south. So if I kind of draw an arrow towards that south, this is the direction of the magnetic field. And so we have this this situation where we have the magnetic field from north to south, the velocity vector here, and then so if you just took your hand right now and kind of oriented in front of the screen a little bit so that your fingers basically point kind of into the screen, your thumb points kind of to the right, you can see that there would be a force in basically the downward direction on the charged particle as it moves this way. And again, because they're trying to show this as a three-dimensional picture, you got to be careful. But the key thing here is the magnetic field is in this orientation. The velocity vector is this way. Those two things are going to be 90 degrees to each other. Right? That's a 90-degree angle. And then the force is this way. And the force is 90 degrees to both of those. So you end up with this little corner. If you connected the tails of all these vectors, you end up with this little box in the corner. So let's go back to this example then. So here's our picture. We have the electron. I want you to predict if the electron is moving from left to right and it comes into this magnetic field that is from the bottom of the page to the top. What does the hand rule tell you would be the direction of the force on this electron? And once you identify that, you should be able to predict which way the electron will be deflected. This is the direction of motion in the green dotted line. What happens to the electron as it enters this magnetic field? Take a second to think about it. Pause the video if you like. Use your left hand and try and predict the direction of the force on this electron. So use your left hand rule appropriately. You should end up with your fingers pointing in the upwards direction towards the top of the screen, top of the page. Your thumb should be pointing from the left to the right. So if you're like me right now, you're holding your hand in front of the screen, your fingers are pointed up, your thumb's pointed to the right. I'm looking at an L right at me right now. And as a result of that, my palm is indicating that there will be a force acting on the electron that will push it into the page. So as the electron enters this region right here, it should feel a force that pushes it into the page. So if somebody said, well, let's represent that as a vector, I would draw the vector as this thing went into the page. I would draw the vector maybe as this X. If I had to, I'd say well, the force vector, F, is into the page. Now, if that makes sense, what's interesting is the result of this, which is that we have a dynamic situation. As soon as a charged particle enters a magnetic field, it begins to feel a force, and that force will accelerate and will cause it to change direction. Consider this for a moment. Your palm says that the force on the charged particle is always perpendicular to the direction that the charged particle is flowing. And that occurs even as the direction changes. The result is this: circular motion. The center-seeking force is supplied by the magnetic force on the charged particle. Consider for a second what happens to the direction of your thumb if you have your palm out and you have your fingers pointed in the upward direction. Tell you what, let me grab the video here for a second. I'll show you what I mean. Consider for a second what happens if, as the charged particle enters a region where the magnetic field is up in this direction, as the charged particle, better yet, let's go this way. I'm going to make the magnetic field go into the page, so my fingers are pointed at you. So as the charged particle moves along, here's the direction of the charged particle moving from left to right, and my fingers are always out of the page. Then my palm shows that the force will always be down, or at least initially down. So watch what happens as my palm, as the charged particle moves to the right, the direction is it's going to feel a force. And so as a result, it's going to get pushed down. Now, my thumb adjusts a little bit. If it starts to get pushed down, then my thumb is going to point down a little bit, but my fingers and my palm stay in the same orientation. So you can see what happens is, as my thumb, the velocity vector starts to change, so does the direction of the force, because the magnetic field stays consistent. And the magnetic field is always 90 degrees to the motion. This is classic case of circular motion, where we have a force that is always perpendicular to the motion. So, in conclusion, because of the fact that a charged particle, let me give myself an electron here, because a charged particle has a magnetic field around it, as that charged particle begins to move, if it moves through a magnetic field, let's give myself a magnetic field in this region here that is, let's say, for example, we'll give ourselves a region here that is, with all these circles, let's just say it's out of the page. So here it is here, out of the page. Poorly drawn, but you get the point. Boom, boom, boom. As this charged particle begins moving into this magnetic field, it's going to feel a force on it. Now, according to my left-hand rule, as it moves to the right and my fingers point out of the page, I should end up with a force on this thing that is in the upwards direction. And the result of that is this circular motion, at least for the part of the motion where it's in this magnetic field. So I get some sort of radius of motion here. So again, the result of this left-hand rule for this negatively charged particle, and oh, by the way, this is important. Now we can see where a right-hand rule would be handy as well, because as a proton, now we're not stuck in wire, so now we can shoot a proton through space. As a proton enters a similar magnetic field, one in which it's out of the page, you can imagine what happens here. As this proton enters this magnetic field, now we are going to use our right hand, fingers out of the page with our right hand, thumb pointed from left towards the right, and now this, no surprise, I guess, in a way, this particle, being oppositely charged, positively charged, also will travel in a circle with a certain radius, all right, because of this hand rule. So again, left hand, big reminder now, because if you thought, oh, I'll just use the left hand all the time, now you will be forced to use the right hand whenever we talk about positively charged objects. For example, a proton, but it also could be an alpha particle with its charge of 2+. All right, so we're going to stop there. We'll get into the mathematics of it for now. Understand the two big concepts here. How do we predict the force on a charged particle moving through an external magnetic field? And how that hand rule kind of dictates or determines for us that when this happens, we'll have a charged particle exhibiting circular motion.